All right, I have shared my screen. Please, somebody confirm that you are able to see and that my voice is clear. Okay. All right, thanks. So we will have our second tutorial today at 2 p.m. So we have, I remember we had one question left from PS1, and then we will see questions from PS2. So in the last class, I made a couple of derivations towards the end. First was rate of fractional change in length of that edge of our fluid element, A, B, C, D, E, F, G, H. Change in length of that edge, which is along E1 at time t. So AB is along E1 at time t. So this is how this is what it means, what I have said in words. Length of AB at t plus delta t minus length of AB at t divided by length of AB at t, and in the limit delta t going to 0. And I showed the steps in the last class. In this limit, it turns out to be a very simple expression. Del v1 del x1, partial of one component of velocity with respect to x1 at time t and at the location where fluid particle A is at time t. SI unit will be per second. And then I also showed you the steps. It showed this part in a little hurry, but the ideas are very similar for the second part also. And since the notes are there with you, I am hoping that once you read that, you will be able to understand. So this was the final result that we got. Rate of fractional change in length of that edge of Fe, which is along E2 at T, which is edge AD. And again, we define that in this manner, where my cursor is moving right now. Length of AD at time t plus delta t minus length of AD at t divided by delta t. And that expression simplifies to del V2 del X2. So there is indeed a pattern when you are talking about that edge, which was along E1 at time t. You get del V1 del X1. So both indices are same, and that same index is the same. That same index is corresponds to the unit vector along which that edge was at time t. So when you go to another edge which was originally along two direction, you get del V2 del X2. All right, so these two results we had yesterday. And I want to remind you, we are still considering that simple case in which I have assumed that the velocity field is two componential. There was no V3 component, and it is also two dimensional. So there is for V1 and V2, there is no dependence on the third coordinate x3. Next question I want to ask is, we want to find the rate of fractional change in the volume of the fluid element. How do I define this? The definition of this quantity, what I'm putting in words is this: limiting value delta t going to 0, volume of the entire fluid element at t plus delta t minus volume of the fluid element at t that is change in volume, and then I am interested in fractional changes. So I divide this change by the volume of the fluid element at time t itself, and by delta t, because I want rate of change, and limit delta t going to 0. We want to derive an expression for this. Okay, now since delta t is small, same argument which I was using yesterday, and consequently delta alpha and delta beta are small, then we can say that volume of fluid element at t plus delta t, we are going to approximate at t plus delta t as length of AB, length of AD times delta x3. All right, so volume at t plus delta t to the first order, this is the approximation that you are actually ignoring the small angles. I mean, initially all faces were at 90 degrees. Now they are not at 90 degrees, but they are very close to 90 degrees still, because delta alpha, delta beta are very small, and that's why this we are approximating volume as simply length of AB, AD, and delta x3. And recall, delta x3 is the dimension of the fluid element in the third direction. And in this case, when we have assumed two componential and two-dimensional velocity field, delta, nothing happens to delta x3. I mean, that length of the fluid element in the third direction remains the same at t plus delta t. Okay, so this is first approximation here. And then I am going to further approximate AB and AD in terms of, in a way that I did yesterday for finding fractional changes in length. I am going to, again, referring to this figure, what you have on the right-hand side, lower part, I drop perpendicular from B on E1 axis, and I drop perpendicular from D on E2 axis, and the points of intersection, I name them M and N. Then I say that length of AB cosine delta alpha is actually length of AM, and length of AD cosine delta beta is length of AN. Since cos delta alpha is approximately 1, it means that I can approximate length of AB as length of AM, length of AD as length of AN. Okay. So volume of the fluid element at t plus delta t can be approximated as length of AM times length of AN multiplied by delta x3. Yesterday I was watching our lecture video, and I realized that some of the diagrams that I put on the slides, they were not very clear on the recorded screen, like these indices x1, x2, x3, x3. I mean, these small annotations here. My suggestion is, if you do not see, if you are watching one of our videos and if those things are not clear, then please refer to the notes also, PDF file. There you can zoom and get a clearer picture. There's not much I can do on the screen because I have already put it to the maximum possible, which can cover the full slide. If I make it larger, something will go out of the screen. So I can't improve it any further right now, but later you should use PDF files to see the expanded fonts. Okay, so this is the volume. This is how we are going to approximate the volume, length AM, length AN, delta x3. So the next job is to find length AM and length AN. And to find that, what do we do? Length AM, this we did yesterday also. Length of AM, I can approximate as 1 of B, which is 1 coordinate of B minus 1 coordinate of A. And length of AN will be 2 coordinate of D and 2 coordinate of A. Going back here, 1 coordinate or length of AM is 1 coordinate of B minus 1 coordinate of A, and length of AN is 2 coordinate of D minus 2 coordinate of A. And 1 by 1 I mean first, by 2 I mean second coordinate. All right, so this is how we will get these length AM and length AN. And I have skipped a few steps here. but this is identical to what we did for fractional changes in length. So I have written the expression directly. 1 of b minus 1 of a turns out to be this, what I have written in green, what I have encircled in green color here, that is 1 of b minus 1 of a, and 2 of d minus 2 of a turns out to be what I have in this purple circle or purple curve within the purple curve. Okay, so we have product of these green, this purple, and of course there is delta x3 which is sitting here. So that would be the volume, approximate volume of Fe at t plus delta t. So now when we expand this, we get these 4 terms, and each one has delta x3 sitting with it. So first term is delta x1, delta x2, delta x3. The second is del v1, del x1, delta x1, delta t. And then I'm multiplying it with x delta x2 and so on. So you can follow these term by term product. So you see that one term has even delta t square, right? That will come because the second term from here and second term from here, that product will have delta t square. So we have a higher order term in delta t. Okay. So I've labeled these terms as 1, 2, 3, and 4. And I'm now going to plug these again in this expression, which is the rate of fractional change in volume. And again, reminded that volume of fluid element at T is nothing but delta x1, delta x2, delta x3. So the second term in the numerator and the term in the denominator, they are just this product of delta x1, delta x2, delta x3, and this purple bracket gets contributions from 1, 2, 3, and 4. That's what I have written here. Okay, one term will get cancelled out. The initial volume gets cancelled out. One gets cancelled out with this initial volume here. It comes with which comes with a minus sign. You are left with 2, 3, 4. But then in the limit. Okay, and then it has to be divided by delta x1, delta x2, delta x3, and further when you impose the limit of delta t going to 0, you will realize that that limit is simply del v1, del x1, del v2, del x2. So this term, which comes with quadratic delta t square, in the limit of delta t going to 0, that will go to 0 very fast. So that is inconsequential in the final answer. Okay, and you see we are getting contribution from both indices 1 and 2. So there is some volume change because there is change in length of AB, and there is some change in volume because there is change of length in AD, and both of them add in a linear fashion in this limit of delta t going to 0, and this is what we get. And again, the SI unit will be per second. Per second because it is fractional change in volume. So there is no meter cube coming because we have taken fraction. It's just per second. And that is consistent with what quantity you have here. Gradient of velocity or derivative of velocity meter per second divided by meter is simply per second. So both physically and the expression wise, we are getting consistent units. Okay, in yesterday's class, how did we prove that the cross section would be a parallelogram? I did not prove it. I just put a side comment, and let me bring that slide. Then I'll tell you what is the argument. So I gave sort of a hint, and you can prove it yourself if you wish. See, this is what I was showing. What I'm saying is that at t plus delta t, this is the state of ABCD. And in yesterday's class, we found expression for delta alpha and delta beta, right? The angles that AB and AD make with E1 and E2 axis. what I was saying, that you can, if you want, you can show that the angle that CD makes, which is opposite to AB, the angle that CD makes with even axis, you can show that that is also delta alpha. And similarly, you can show that the angle that BC makes with vertical in D2 direction, that is also turns out to be delta beta. When I say delta alpha and delta beta, I mean this. So for delta alpha, uh, this is the expression we got. This is the expression we got, delta alpha, and delta beta, we got this expression, right? So when you work on these angles, as I said, angle of CD with E1 and angle of BC with vertical E2 axis, they will also turn out to be same as delta alpha, delta beta. And based on that, you can conclude that the distorted form is a parallelogram. Okay, so I did not show it, but what you can see. Have I answered your question? Yes. Okay. All right. Okay. So to summarize, we have found rate of change of fractional volume, rate of change of fractional lengths, two sides. We have found rate at which two sides AB and AD are collapsing towards each other. And we found an expression for the averaged angular velocity. And if you go back to my previous lecture, those were the questions I raised in the beginning of yesterday's lecture, and we have answered those questions. But those answers are for the case when the velocity field has been assumed to be two componential and two-dimensional. So it was a good exercise. I hope that gave you insight and also made you aware how to approach finding such expressions. Now we are going to now what we want is we want expressions for the same questions, but relieving ourselves of that those two constraints, that velocity field is two componential and two dimensional. We want to go to a general flow field, and what I will do is we will use the results derived so far, okay, and extend those relationships for a general flow field of the form which is completely generic, so be three componential and three dimensional. Now, the way I'm going to extend the result, I'm going to use pattern recognition. I'm not going to derive, as I told you earlier, the algebra becomes a lot. If you want, you can do it yourself. But right now in this class, I will do pattern recognition and extend it. We consider, so with this velocity field, general 3D and three componential velocity field, again, I consider this same fluid element, which I've shown here on the right hand side. A, B, C, D, E, F, G, H, with vertex A at x1, x2, x3 at time t, and all adjacent edges mutually perpendicular to each other at time t. Further, dimensions of the fluid element are delta x1, delta x2, x3 as before, and these edges are being parallel to E1, E2, E3 respectively. So same situation. Now, couple of things we need to acknowledge, that now that since V3 is not equal to 0, so all fluid particles which are part of our Fe, our identified fluid element, will now have the freedom to get displaced in E3 direction as well, right? Yesterday, a student asked the question, and when I was answering, I addressed this yesterday also, but for for the benefit of the entire class and to put on notes, I have made these statements. V3 is not equal to 0, so all FPs can move now in E3 direction, which was not happening earlier. Further, since V1, V2, V3 are three-dimensional, dependent on, which means dependent on x1, x2, x3, when A, B, C, D, for example, when A, B, C, D, they get displaced by their local velocity vectors, and then the resulting position that they will achieve at t plus delta t They at t plus delta t, they will, in general, they will not be in a plane which is parallel to x1 e1 and x2 x2 e2. Okay, so yesterday it was happening that ABCD were getting displaced, but they were still confined to a plane which was parallel to x1 e1 and x2 e2, right? But now with this three component shell and three-dimensional velocity field, that is not guaranteed. They will not be lying in the same plane. They will not be lying in a plane which is still parallel to x1 e1 and x2 e2. Okay. So I have tried to draw here to the best of my drawing ability. I've tried to show that fluid state of that fluid element at t plus delta t in a general distorted state. Okay. And I'm trying to show here that ABCD, that plane in which ABCD are lying, that plane is not necessarily parallel to the original plane or parallel to the plane of E1 and E2. Okay, they will make a plane actually which is inclined at some angle to the plane of E1 E2. Okay. So even though I said I will do pattern recognition, I have tried my best to give you some more insight so that you can, if you want to derive things, you can follow some steps. So with that attempt, last night I added a few more things in my notes, and what you see here. I have used some colors and some primes here to convey that the way to derive the new expressions, if you want to fully derive, is to recognize that recognize these projections of various edges on three planes, E1, E2, E2, E3, and E3, E1. Okay. So you see on the left side, left bottom side, these are the three edges I am focusing my attention on: AB, AD, and AE. Okay. These are the three edges we will focus our attention on. When we were having the 2D two componential case, there were two edges we were focusing on, right? AB and AD. And with that, we were able to answer all the questions that we asked. Since it's a general 3D three componential field, besides AB and AD, AE will also be of relevance, edge AE. Okay, so you see that these green dotted lines, what I'm showing here, they are the projections of, okay, so AB triple prime is the projection of edge AB on plane E1 and E2 at time t plus delta t. So everything on the right hand side is at t plus delta t. So AB triple prime is the projection of edge AB on the plane E1, E2. Okay, I have put these three primes. I'm trying to kind of make a nomenclature or a notation scheme so that it becomes more logical. I put three prime because I'm trying to say that this is the projection of B. So three primes mean the projection of B on a plane which is perpendicular to three axes. And of course, that plane is E1, E2 plane. Okay. Similarly, AD triple prime is the projection of edge AD at time t plus delta t on a plane which is perpendicular to E3 axis. Okay. So AP triple prime and AD triple prime, of course, are now lying in the plane of E1, E2. Okay. Similarly, AD prime is the projection of edge AD on a plane which is perpendicular to E1 axis. So 1 prime means E1 axis. And similarly for E prime. So AD prime and AE prime are projections of AD and AE on a plane perpendicular to E1. And extending the same idea on the third plane, the relevant projections for our derivations would be AB double prime and AE double prime. They are projections of AB and AE on a plane which is perpendicular to two axes. That's why 2 prime. Okay. I have written here also these projections of edges on the plane perpendicular to E1, E2, and E3. Okay. So with these projections, now we can associate angles. Remember, we had delta alpha and delta beta in 2D case, 2D two componential case. Now we will have several delta alpha and delta beta. In fact, 2 angles on every plane. So in that way, we are dealing with 6 angles. Okay. And since we are dealing with the new multiple delta alphas and delta beta, again, I have taken the freedom to put a subscript with the intent that it conveys the meaning. So what is the meaning here? If you go to E1, E2 plane or a plane which is perpendicular to E3, I am denoting that delta alpha. Earlier it was just delta alpha. I am putting now index delta alpha 3. 3 means that it is delta alpha belonging to a plane which is perpendicular to the third axis. And similarly, this angle becomes delta beta 3. Earlier it was just delta beta. Now, following this notation scheme, I am the delta alpha that you see here. I mean angle of AD prime with E2 axis, I should call it delta alpha 1. And the other angle AE prime that is made with E3 axis should be called delta beta 1. And similarly, the angle that AB double prime makes with E1, I'm calling it delta beta 2. And the angle that AE double prime makes with E3 axis, I call delta alpha 2. So these would be your initial steps if you want to do full derivation. All right. All right, so having recognized these angles now, the pertinent questions to ask here will be rate at which, one may ask this question now, rate at which projections of AB and AD on E1, E2 plane are collapsing towards each other. Effectively what I'm asking, rate at which AB triple prime and AD triple prime are collapsing towards each other. Okay. And based on the notation, angle notation, that should be limiting value delta t going to 0, delta alpha 3 plus delta beta 3 divided by delta t. Okay. And now if you wish, again, I'm not forcing you to do this. I'm not doing it in the class, but if one wants, he or she can show that this will be in the limit of delta t going to 0 will be del v2 del x1, del v1 del x2. So even though now velocity field is 3-dimensional and 3-componential, as far as projections AB prime, AB triple prime, and AD triple prime are concerned, their rate of collapse is governed by derivatives 1 and 2 and velocity components 1 and 2. Okay. Again, what we did yesterday, this was the only question as far as collapsing rate is concerned. But now, since it is 3-componential and 3-dimensional, we can ask 2 more similar questions of edges collapsing or projections of edges collapsing. The next question I can ask, rate at which projections of AD and AE, remember AD and AE, AD was originally along 2 axes and AE was originally along 3 axes. So rate at which projections of AD and AE on E2, E3 plane, E2, E3 plane are collapsing towards each other. So effectively, I'm asking rate at which AD prime and AE prime are collapsing towards each other. Looking at the symbols here, that is this limit with alpha 1 and beta 1, or delta alpha 1 and delta beta 1. And you can show that that will turn out to be velocity component 3 and 2 being involved, and derivatives, I think I made a mistake here. It should be del v2 del x3. I'll correct this. Okay, and again, this pattern is actually coming from if it is on E2, E3 plane or edges which were originally along E2 and E3, then only those 2 indices are going to play a role here. and in a crossed fashion. Crossed fashion means if v is 3, x will have 2, and if v has index 2, then x will have 3. And the third similar question I can ask, rate at which projections of AE and AB, AE and AB are projections of AE and AB on E3 even plane are collapsing towards each other. And since 3 and 1 are involved, we will have del V1 del X3 and del V3 del X1. Okay. So now with this general expression, if we want to go to two-componential and two-dimensional, you can see that the last two questions will have trivial result 0, either because V3 is 0 or because nothing changes in the third direction, right? For example, this one, if I take this expression to the take this expression back to what we had, the kind of velocity field we had yesterday, first term will be 0 because there is no V3, it is identically 0, that's what I told you. And second term will be 0 not because V2 is 0, V2 was non-zero, but then I said that V2 is two-dimensional, V2 has no dependence on the third coordinate, so the second term will also be 0. So in that fashion you can reason out that the answers to the last two questions would be trivial in a velocity field having two componential and two-dimensional velocity field, in a flow with two componential and two-dimensional velocity field. All right. So these are some physically relevant questions we asked, and we get expressions for them. Okay. So the second type of question that we were interested in, you remember at what rate the fluid element is rotating, and I defined a quantity averaged angular velocity, but then we defined it only for delta alpha and delta beta for the problem that we had yesterday, and this is what we derived yesterday for two-componential two-dimensional flow field. And I also highlighted yesterday that that would be the third component of the average angular velocity. Now with the general flow field, three-componential, three-dimensional, you will have velocity, angular velocity components in other two directions also. And again, I'm leaving the detailed derivation. I'm relying on pattern recognition here. And with this expression, what you derive, you can actually generate the other two by letting 1, 2, and 3 change in a cyclic fashion. So if you are going from, this is E3 component, if you want even components, so 3 you make 1, of course, you want even component. 2 I would make as 3, that's what you see here. Cyclic manner, 2 you make 3, that is what you see here. 1 becomes 2, that's what you see here. I mean, I'm comparing the third, I'm trying to generate the first component using the third component, and then minus sign will remain, 1 will become 2, that's what you see on the left, on the first term, I mean even component, second term of the even component, and 2 will become 3. Similarly, you can generate the second component. So this will be the full angular velocity vector with its 3 components, averaged angular velocity of the fluid element. And remember, angular velocity is always associated with fluid element. It will be a wrong statement to make that average angular velocity of a fluid particle is this much. It doesn't make any sense. It has to be of a fluid element, not particle. All right, so this is the rate at which fluid element is rotating. Now the other questions also we can answer based on pattern recognition. The other questions, relevant questions for the fluid element, are rate of fractional change in length AB. What is AB? AB is the length edge which is parallel to E1 at time t. That's what AB is. And you will get del V1 del X1, which is the same as before, 2D case, 2D2 componential, excuse me, 2D2 componential case. I can ask the question, rate at which rate of fractional change in length AD. AD is the edge which is parallel to E2 at time t. That turns out to be del V2 del X2. So 2 from this E2, same index with V and same index with X. Similarly, rate of change of length AE. So AE is the edge which was parallel to E3 at time t. Turns out to will turn out to be del V3 del X3. So that's about fractional change in lengths. And the last question, last relevant question for us is rate of fractional change in volume of the fluid element. And that turns out to be what I have. So earlier it was del V1, del X1, del V2, del X2. We stopped there. But for the general flow field, there will be another contribution coming from del V3, del X3. That will be the rate of change of rate of fractional change in volume of the fluid element. Now, this is also called, in some texts, it's called dilation rate of fluid element. Dilation rate of fluid element, right? Now, notice that this expression, del V1, del X1, del V2, del X2, del V3, del X3, when added together, that actually can be written in tensor notation as del dot V. I think I gave this. This is one of the problems on problem set 1, where I asked you to write express del dot V in Cartesian coordinates, and the answer is del V1 del X1 del V2 del X2 del V3 del X3. Okay, and this is called divergence of velocity vector. I think in the second, third lecture I said del dot V is del dotted with any tensor will be called divergence of that tensor. So in this case, the tensor is velocity. So this can be called divergence of the velocity field. And talking about physical meanings, students were curious, what is the physical meaning of divergence or something else? So here is an example. If the tensor is velocity, and we are talking about fluid mechanics, then the divergence of velocity field mathematically means this. But what we have seen so far in last 2 lectures, it has a very nice physical meaning. The physical meaning is rate at which rate of fractional change in the volume of the fluid element, of a small fluid element. Okay, so such physical meanings will be coming our way once in a while, and I will try my best to keep highlighting them. This is yet another example. So we saw an example of advection operator last week. Now we have divergence of velocity field has a physical meaning. Okay. So you have noticed, you must have we have been seeing. I mean, it's clear even on this slide that all these answers have to do with gradients of velocity, or I should say derivatives of velocity. So that reminds me of a quantity del V, which should be called the velocity gradient tensor, right? There is no dot, nothing in between. Del acting on V. So that should be called velocity gradient tensor or gradient of velocity. Now, in Cartesian coordinates, we have seen this. I took this as one example, I think, in lecture 3 or 4. Del V, if you expand in a Cartesian coordinate system, this is how it will look like. This is how it will look like. You have 9 components along the 9 members of the second order basis or second order dyad, 1, 1, 2, 2, and so on. And I hope you remember that the indices have to be in particular order. So the first unit vector, the index of the first unit vector of the dyad should match with what goes with the derivative. And the index of the second unit vector of the dyad should go with the component of velocity. So this is what it will be. So whatever quantities we have derived so far, last 2 lectures, we derived based on their physical meaning and applying Taylor series and basic calculus. And what we realize now that these quantities all the final answer seems to be various components of this velocity gradient tensor, right? You see del v1, del x1, del v2, del x1, all those components are members or components of velocity gradient tensor. So in a way, we can now associate various physical meanings. We can associate physical meanings with various components of velocity gradient tensor as well. But before we do it, before we make it more formal, I want to split the velocity gradient tensor into a symmetric and anti-symmetric part. Okay, so I'm defining two new tensors using the velocity gradient tensor as this. Again, this I mentioned in lecture 3 while talking about tensors that given a second order tensor, you can always create a symmetric tensor out of it by doing this operation, adding transpose of that to itself and dividing by 2. That should give us a symmetric tensor, and we can always get an anti-symmetric tensor by subtracting out the transpose from the original second order tensor. So in this case, the second order tensor is velocity gradient. So the symmetric tensor is called, in fluid mechanics, we call it strain rate tensor, strain rate tensor. And I will use the symbol S with an underbar to denote it is a tensor of order greater than 1 in general. But in this case, we know it, the context is clear that it's a second order tensor. And we have the anti-symmetric tensor that we have created with the velocity gradient tensor. We call it rotation rate tensor, rotation rate tensor. And I will use the symbol W. Now, since S is the symmetric tensor created in this fashion using velocity gradient tensor, you can easily show that S will have these components, what I have written here, bottom left part. One component of symmetric tensor is del v1 del x1. Actually, it is del v1 del x1 plus del v1 del x1 divided by 2. So that is just reduced to del v1 del x1. Similarly, coefficient of 2, 2 and 3, 3 will be del v2 del x2 and del v3 del x3. Whereas components of E1 and E1 E2 will be del v2 del x1. That contribution is coming from here, del v. And then the other contribution, del v1 del x2, the transpose part comes from this. And then I divide by 2. And similarly, the other terms. So I hope if you look at it, you can reason out why these terms should be like this. And similarly, if I now try to cast the rotation rate tensor in this Cartesian coordinate system, it will turn out to be what I have written here. And you will realize since it is an anti-symmetric tensor, its components of 1, 1, 2, 2 and 3, 3 are going to be 0. And other components are going to be governed as this del v minus del v transpose according to that formula. So for example, component of E1, E2 will be del v2 del x1, which is coming from del v, and then minus del v1 del x2, which is coming from del v transpose, and then a factor of half. And since it's an anti-symmetric tensor, W12 should be equal to minus W21, W13 should be minus W31, and W23 should be minus W32, which you can again verify indeed that is the case. And strain rate tensor being symmetric, you can also recognize from what I have at the left bottom that S12 is S21, S32 is S23, and S13 is S31. We will be using these tensor very often in fluid mechanics. Almost all the time you will be talking about strain rate tensor and rotation rate tensor. So my idea was that at least for one time I show you the full tensor here, and then we will be referring to its components later on. Okay. So what you can recognize at this stage is that for example, del v2 del x1 plus del v1 del x2 by 1 by 2, which is the component S12 of tensor S, we have that has a physical meaning, right? Rate at which two edges are collapsing. Of course, there is not the factor of half is not there, but apart from that factor, keeping that factor aside, this is the rate at which projections of AB and AD are collapsing towards each other. Okay. Then I also encourage you to recognize that the rotation rate tensor, the expression that we have gotten here, that can be written in terms of the average components of the average angular velocity as well. Average angular velocity was omega. So you can see that, you can recognize that these terms are also the components of omega, and thus the rotation rate tensor can be written in terms of omega components. The rotation rate tensors can be written as components of average angular velocity. Okay. So now working with S and W, strain rate and rotation rate tensor, we recognize that the rate of fractional change in AB is nothing but the S11 component of strain rate tensor. Okay. Similarly, rate of fractional change in AD is the 2,2 component of strain rate tensor, and rate of fractional change in AE is the 3,3 component. Again, AB, AD, AE, I'm referring to the same fluid element that we have been considering. So we have considered so far. And the dilation rate can be written as the sum of the so-called diagonal components of strain rate tensor. Diagonal components, I mean coefficient of 1, 1, 2, 2, and 3, 3. And that is same as dilation rate, right? Because that is, you see, del V1, del X1, del V2, del X2, del V3, del X3. That's what we derived earlier. Now here, a piece of information. If we have a second order tensor, then sum of the coefficients of 1, 1, 2, 2, and 3, 3 is also sometimes called the trace of the tensor. Okay. So if you have a second order tensor, you take the coefficients of 1, 1, 2, 2, and 3, 3 and add them together. That is also called the trace of the tensor. And you will see in some books they write it like this: trace of tensor S. What it means is S11, S22, S33. Okay, so we can say that the trace of the strain rate tensor represents dilation rate of a fluid element or fractional change in rate of fractional change in volume. And as I was saying earlier that so effectively what I'm doing here is I have defined two tensors, strain rate and rotation rate, and I'm now trying to associate physical meanings to the components of these two tensors, various components of these two tensors, right? So strain rate tensor, 1, 1 component is rate of fractional change in AB, 2, 2 is rate of fractional change in AD. Similarly, now if I come here, 2 times S12, 2 times S12 represents rate of collapse of projections of AB and AD on E1 and E2 plane. So we can make sentences based on what we derive. All right. Similarly, twice S23, 2 times the 2, 3 component of strain rate tensor has this meaning what I have written here. And similarly, 2S31 has a physical meaning. Then another way of referring to these components is what we call as normal and shear strain rate components. You might be hearing similar phrases in the solid mechanics course: normal strains and shear strains. Of course, there are no rates involved there because there is no change in time. Here we talk about strain rate and rotation rate. Time derivatives are involved. So 1, 1, 2, 2, and 3, 3, sometimes they are referred to as the normal strain rate components. Normal strain rate components. And S1, 2, S2, 3, and S3, 1, they are referred to as the shear strain rate components. So shear has different indices, normal has same indices. So my overall conclusion is that different components of del V tensor has different physical meanings. And then we have split, instead of dealing with del V or velocity gradient tensor, we many times we deal with symmetric part of the tensor or strain rate, or sometimes we deal with the anti-symmetric part, rotation rate. And my idea behind all these last 2 3 slides is that uh, there are physical meanings that we can associate with different components of strain rate and rotation rate tensors. Okay, I'll take a couple of minutes and stop. Um, okay. There is a relationship between the omega vector, which is the angular velocity vector, and this quantity del cross v. You may remember that I said del cross v is called curl of the velocity, curl of the vector on which it acts. In this case, it is acting on velocity vector. You can show that the angular components of the average angular velocity, which we derived from physics of the problem. I mean, I drew a fluid element and drawn edges and then derive things based on that. So whatever expression we got for angular velocity vector, we can show that they are actually related to the components of del cross V. So in literature, sometimes people will talk about components of omega, and sometimes they will talk about components of the curl of the velocity vector. And it turns out that they are related uh, with they are related to each other in this fashion, what I'm showing here. So if you find the one component of the curl of velocity, that turns out to be 2 times the first component of the averaged angular velocity. So there is a factor of 2 between components of angular velocity and components of curl of velocity. All right. So this is to expose you to these ideas. I mean, these are like definitions only. I mean, I'm just sharing some information. There is no analysis or derivation involved here. These are just quantities which are related to each other like this. So components of del cross V and omega are related. And then you can also show that I've already shown this, that components of average angular velocity are related to the components of the rotation rate tensor. All right. Let me see what I have here. Yeah, so I will end the class with this statement that all these quantities that we have seen in today's class, S, omega, del cross V, W, they're all tensors. We can choose to express them in any coordinate system of our choice. So far, we have used Cartesian coordinate system. If we go to a different coordinate system, their components will become different. We have visited this idea many times so far. In a different coordinate system, their components will become different, but the tensors will remain the same. All right. So next class, what I will do is I will try to see. We will try to see what how the components of these tensors look like in another popular coordinate system, which is cylindrical polar. All right. Again, because we do use cylindrical polar coordinate system once in a while, so it's good to get familiar with the components of these quantities in that coordinate system as well. That I will do tomorrow. So I stop here. If you have questions, you can please write on the chat box. Can you explain how the average velocity vector gives us a sense of rotation of the fluid element? Okay, I'll make an attempt. So I'm taking this slide, showing this slide to you, which I used in yesterday's class. So if the body is rigid, the body is completely rigid, then this expression will hold true, right? All line segments will have the same rotation rate, and you can pick up any of those line segments, find at what rate they are changing orientation, and that will be the angular velocity of that rigid body. Okay. In the case of fluids, since it is deformable, two line segments will not have the same angular velocity, right? So that's why I put delta alpha and delta beta. Now the way I do delta alpha and delta beta, if I add them, they tell me that how fast those two angles are collapsing towards each other. Now, if I take the difference out of them, it actually tells me, and it is very qualitative. The way I am telling you is, it may sound very qualitative, but you have to think about it, that when I take the difference, that is telling me that if I ignore the collapsing tendency, then at what rate side AB and AD, they try to move, try to rotate in the same sense. Okay, so delta alpha minus delta beta will tell me what is the extent to which AB and AD, without collapsing towards each other, tend to rotate in the same sense, going from both try to go in the counterclockwise in the same sense, right? The difference tells me their tendency to go in the same, rotate in the same sense, which in this case is counterclockwise. All right, and that's why I say it is giving us a sense of rotation. Had it been a rigid body, this would have reduced to, had this been a rigid body, this expression where my cursor is right now, this would reduce to d alpha dt or minus d beta dt, which is precisely the angular velocity of a rigid body. So in the limit, so if I put it alternatively, in the limit of the body being rigid, the omega 3, the way I have defined this, indeed represents the rate of rotation of the body where we are focusing. So in that way, I'm saying it gives us a sense. The limiting behavior of this expression takes us to what is there in rigid body and what we call as the angular velocity of the rigid body. I don't know if it has been convincing or not. Yes or no? If no, I will make some more attempt, or I will think about it more and try to put the ideas in words later. Okay. Yeah, so it's the limiting value. I think you think in terms of this limiting sense. That expression which we wrote as omega 3 in the limiting sense is consistent. Limiting sense means the body going to rigid behavior, completely rigid behavior. In that limit, that expression indeed coincides with what is called the angular velocity of a rigid body. And that is why I am saying that this gives us a sense of rotation of the fluid element. I have extended the class, the session. I'll be here. I'll wait for 2 more minutes if you have any questions. And I don't know if you are still there, the person who asked this question. I, mind you, the average, what I am using, the phrase I am using, average, that has to do with the fact that I took two segments and divided by 2. That's why I'm saying it's sort of average. Sort of average over 2 observations. Observe 2 observations on how the orientation of 2 segments are changing. But rate of change of alpha and rate of change of beta are of opposite sign. No, rate of the way I have drawn in the figure, you see that the way I have drawn delta alpha and delta beta, delta alpha is positive in counterclockwise sense and delta beta is positive in clockwise sense. This is how I started my, this is what my notation is. So positive delta beta means actually AD coming towards AB. Okay, sure. Yeah, maybe I'll highlight this in the lecture today. I thought that by showing those arrows, it was clear that which direction they are positive. Since you have asked, I think I should put that. Some other students might not have realized this. All right, it seems there are no more questions, so I'm going to end this session now.